Well, hello, Physics 30s. Today we're going to talk about diffraction and interference. Another one of the properties of a transverse wave. So far we talked about reflection, refraction. Now we're going to talk about diffraction or diffraction, interference, and then the last thing we'll talk about is polarization, which is really easy. You just have to know light polarizes. That's one of the properties of a transverse wave. Not necessarily how it polarizes. The reason behind how light polarizes, how polarized sunglasses work and stuff, and how the lenses in a 3D glasses that you might wear at a movie theater, how they actually polarize the light so that you see the left and right images properly. That's beyond this course. All you just have to know is that light polarizes. If you want to learn more about those, I'll give you little videos to watch, but you don't have to know anything else other than that they polarize, which I might just make one small little video that just says that exact same thing, show a little demonstration of what it is, and then that's it. Polarization. This one's a little bit more, though, diffraction and interference, or diffraction. Diffraction, interference. It's a little bit more intensive, involves a little bit more calculations. It involves a little bit about assumptions as well, about small angles, and a few other little tiny assumptions that we have as well that make some of these formulas not the best formulas in the world. I'll talk about which formula. There's two formulas that we're going to develop for the diffraction or the diffraction here, sorry. One of them we never use for the math. We only use for relationships, like what happens when I change one variable? How does the other one change as well? Then we use one for just the math. All right. So let's go through these. I can't remember, one of the very first videos of this unit when you talk about light as a wave, I think it was a crash course one, they talked about this principle here. I always want to call it Huygens, but I don't think it's actually pronounced that way. Well, they just talk about how all waves are consist of smaller, tiny circular waves, and those tiny circular waves produce a nice flat line or a nice curved line when you add those waves together. And then the idea that all waves are made up of these tiny little waves allow the waves to bend around things. So say we have this kind of picture here. Okay? So you got this flat wave, but this flat wave is just made up of a bunch of waves. Okay? And when it passes through, the waves, these parts of the waves here, these kind of get canceled out. So these two other waves here, they're passing through here. They're passing through, they're going through, but when they come to this side here, just like a ripple in a pond, they're going to move in all directions. So it's not going to just be a flat line. They're not just going to do this all the way through. They're actually going to start bending slightly around to complete this circle. And there's no other wave there to interfere with it on either side. So these guys are gone over here. So they'll just keep on bending ever so slightly more than the other ones there. And then if it bends outwards, it's going to bend a little bit more, a little bit more. We still have this shadow area here where there's nothing there, so a little dead spot. But the wave will bend around. This is apart from reflection, this is one of the main reasons why you can hear people in the hallway and stuff, right? Because the sound waves are going to bend around the corners. They're going to spread out as they pass by an object. This is also the reason why there's dead spots when you're driving around Alberta. So say you drive down a valley. So you're in the valley down here. Right? You may not have a radio signal, or you may not even have a cell phone signal because the tower in all its glory here, let's just say it looks like that, can only bend so much. The waves coming from the tower, the radio waves or the microwaves, whatever communication waves we have here, may not bend enough, but they do bend. So you don't have to have a line of sight of a cell phone tower or a radio tower to actually hear your cell phone or to transmit information through the cell phone or through your radio tower, because the waves will bend around objects. So you don't need a direct line of sight. You don't have to see those towers. But there are dead spots because sometimes it doesn't diffract as much. But fun thing about this is that waves that have a longer wavelength will diffract more than ones that have shorter wavelengths. You'll see that later on when we get to a formula about interference. Now, when they come through a two slits, we're going to get a diffraction pattern here. Here we just get one big kind of overall wave. This will look like a big wave eventually, look like that. When you get this, you'll get the waves that come out through, but then they will start bending around and they'll start interfering with each other. Okay. And you can see here, you get a crest and a crest all the way down. You're going to get kind of these little bright spots. And I'll show you a video. I'll link a video in the doobly-doo here in the classroom. Veritasium, he goes around and does an experiment like this. He does some other ones too about ripples in water and stuff. But the idea of these waves interfering with each other, producing a weird pattern on the other side, is that's diffraction grating. So Thomas Young's dual slit experiment. But the idea that it bends around an object, or bends around, is called diffraction. So here's a simplified Thomas Young's experiment here. You could either do it with a card, so you just get sunlight, you get a little light of ray going in. As long as you can get that ray kind of getting pierced by the cardboard, where it kind of pierces on both sides and it goes over top of the piece of paper. Then when it comes to the other side, they're going to bend around the other side and start interfering with each other. And you get this kind of interference pattern. Right? You can see this, and I'll try to do a demonstration of it. You can do it with a laser pointer. With a laser pointer. And now a laser pointer, you want to get one single dot with a laser pointer. Can't point that properly, but you get the one single dot. But if you were to put a hair across the top of the laser pointer, you can get an interference pattern like this. Maybe I'll try to show that to you in the next, or in a separate video. Here, I'll put the link in the doobly-doo as well. Okay, the next two slides here, 75 and 76, they're exactly the same. So you just cross one of them off. Gone. Okay, so when you see an interference pattern like this, the bright spots here, we call them a couple different words here. Bright fringes or antinodes, right? Antinodes. Sometimes we call them maximums, right? First order maximums, second order maximums, bright spots, antinodes, they all mean the same thing. And then dark fringes and dark fringes and nodes, we like to call those minimums. So you might see a few different assignments I give you. I use the word minimums for dark spots, and that would be like the pieces in between. So you can see here in this picture that there's a big bright central bright spot here. It's a big antinode, and then there's a kind of a dim spot beside that. So that would be your node point, and then maybe beside another bright spot, there's another antinode. It kind of goes out both ways. Okay. Now, some nomenclature about this is that that center one, if you go to page 78 here, that center bright spot, which is always going to be halfway between the two bright spots, we always call that the central one, that is actually N0. We call that another N, not the same N as in index of refraction or any other N's that you might have seen. These ones are just talking about which bright spot am I talking about. It's an N value just for that. So the center one, we just call it 0. And then you can see they put some other numbers here. Like there's another one here for 1. That is the N value for that next bright spot. That's N is equal to 1. This next one is N is equal to 2, etc. Now dark spots, dark nodes here, they have half N values. Yeah. So like between 0 and 1 here, this one would be a half. That's its N value, right? On either side, there's no negative or positive here. It's just a very symmetrical picture. So sometimes we only talk about the one side of it. I know it's kind of sideways here, sorry. But those are the half ones. The next one here would be 1.5. The next one here would be 2.5, sorry. This would be 3.5, right? All the way down for the dark spots. Those half numbers. Let me go back up to our picture here. So this is just one of the experiments. Thomas Young did this experiment to give strong evidence that light is a wave because waves interfere. Ripples in a pond, waves in a slinky, they all kind of interfere with each other. So if light does the same thing, it creates this interference pattern, so light must be a wave. Okay, it's really strong evidence that actually it is a wave model. Everything that we talked about so far is pretty strong evidence that it's part of the wave model. Just one second. Okay, so this diagram that you see here kind of helps us explain why do we get these bright spots and these dark spots, these different interference patterns. Why do we get this alternating bright, dark as you go out? Why does this pattern exist? Okay, so what we had to know is that waves, transverse waves, will interfere with each other. Interfere with each other, sorry. And it's called the law of superposition. So if I have two crests, the two crests are going to add up into each other and become one big crest twice the size, if they both have the same thing. If I have a crest and a trough, they're going to add up together and cancel each other out. So that's destructive interference, and the other one is called constructive interference. So the reason we get a bright spot down the middle, like always right halfway between the two bright spots, if I draw a line from the middle of the two slits here, or either side of this piece of paper that he has here, this card, like right down the middle there, you always get this nice little bright spot. Here's my two slits here. Got a slit here and a slit here. I should probably didn't color that. So slit here, slit here. And there's going to be a bright spot right here. The reason we have that is because this distance, and this distance, those two distances are exactly the same. And those two distances are exactly the same, and they're coming from the same source. The key is that you can see here from the light source here, they take one beam out from that they split that beam on the top and bottom. So it's coming from the same source. So they have the same wavelength, they're in the same phase at the same time. So the crests start off in the same spots and the troughs start at the same spots. Everything's the same wavelength, everything just kind of works out. So you can see here they're in phase with each other, so they're both going in this example here, they're both going up to start off with. And then they're going both down at the same time. They both have the exact same wavelengths this way. As they travel the same distance, if they start in phase with each other, it's just in phase just means that the crest and the crest are in the same spots and the troughs and the troughs in the same spots. If they travel the same distance, they will still be in phase down here. So it will be constructive interference by the time we get down there. You can see that a trough and a trough will match up, a crest and a crest will match up. So right here, everything will just match up nicely, and you get constructive interference. So that will be a nice bright spot. Yeah, you'll get a dark spot if they become out of phase. They're completely out of phase too, not just slightly out of phase, because they're just slightly out of phase. Oops. Then you might get a dimmer spot. So like right in the middle is really, really bright, then it kind of tapers off a little bit and gets darker and darker and darker. And it's the darkest when they're completely out of phase. So let's imagine, I'll pick a different color here, purple. This part here, okay? So imagine the same waves, but now they're going to be traveling just slightly downwards here. Now, if I were to try to draw the same wave, this wave here, it's a horrible wave I just drew there. I mean, rather than drawing the wave, I'll just draw a line here. All right, so let's draw a line here. And then draw a line here. The waves are going to be traveling along those two lines, but you notice that the top line is slightly longer than the one on the bottom. And if it's longer by just enough, by exactly half a wavelength, remember a wavelength is from a crest to a crest, or from one point to another point, so half a wavelength would be here. That's a half a wavelength. If I'm off by half a wavelength compared to the one on the bottom, so I'm just traveled just a little bit more than the one below it. If I'm off by that just half a wavelength, then I'll have deconstructive interference. So here, if I were to try to draw the wave here, maybe this wave here by the time I got here was going upwards, and the wave here was going downwards. So I have a crest and a trough, and then a deconstructive, so this would be destructive. Interference. Because the difference between the two waves is off by half a wavelength. If I'm off by a whole half a wavelength, so like yeah, the length, set by length, the differences between the lengths here is off by half a wavelength, then I'm going to have destructive interference. You can see the reason up here you get constructive interference because you're off by a whole number. You're off by 1. If I go down slightly, and maybe the top one had to go a little bit longer and the bottom one had to go a little bit shorter, maybe if I did that one, move down slightly, the top one would be just long enough that it would actually be one whole wavelength longer than the previous one. So I could draw in another one here. Let's go green this time. But further down, maybe if I were to take that bottom line and line it up just on the bottom here, don't want to go about here, but there'll be enough in there to have a whole another wavelength so that things would match up and be constructively interfered here again. And then it'll just keep on doing that as you go because the top line will always get a little bit longer than the bottom one. And you'll get a bright, dark interference pattern. It'll work on the same on the top side too. I just drew on the bottom. Okay, so a few things about this diagram you can see here already drawn is the distance from the slits, down here, the distance from down here. Oh, so that's a bad color to use there. The distance from this screen all the way to wherever you're measuring the picture, that's L. The distance from when the slits end to here, that's going to be L. Right? Usually a pretty long distance too. So that distance from the slits that you're getting the 2 waves out of, because they're coming from one source over here. The distance from that slit to the screen is denoted by the letter L, the length. Okay? The distance between the 2 slits, which is usually a really small number, is denoted by the letter D. Okay? And there's a few other ones in here that relate to a formula that we're going to use. Another thing, like from the center line, always measure from the center, down to whichever node that we're looking to, or antinode, or whatever we're doing here. That distance is called X. Measure from the center to whichever node or antinode we're using. That's going to be the letter X. Okay? And there's going to be some angles in here we're going to deal with as well. There's a formula that involves an angle for the actual formula that we actually have for this. Okay, so before I get into the math of this part, I'm just going to stop the video there so this video is not so long, and then we're going to deal with what's the first formula, how does it work, and what's the second formula, and why we don't use the second formula apart from just talk about relationships and stuff. So I'll see you in the next video. Bye.